Welcome to SolidCAM Professor on a series of Getting Started. I'm Sydney, your SolidCAM Professor, and in this part we'll be showing the machining of this particular part as you see on your screen using HSM, high-speed machining. We will be illustrating our HSM on this particular mold over here. I've already created a home position at the top center of the part. I've already created my stock material and my target, and I already have a part tool table. We'll go through the tool table as we go through the operations themselves. In our first operation, we'll be doing a rough cut around this part to get out as much material as we can. We'll start off with our operations at operations HSM, and we'll start from our list of machining options with contour roughing. Note we already have our MAC position and we already have our target. My tool, I'll be choosing a tool that is a 20 millimeter end mill, and my constraint boundaries will be created automatically around the target itself, and I will be going toward the external of the part. Now let's just go back for a moment for the tools. Let me explain certain things. For example, we have our spins and feeds, but we also have here on our right hand side special feeds that we should pay attention to. For example, we have here something called rapid. This rapid is used for when going from one area to another area using a G1 mode, using the shortest route between areas. We'll go into that area a little later on. We'll talk about that as far as retract strategies. Let's go now to our passes. In our passes, we will leave a thickness offset to the tool of 0.5. You'll note that when I put the value of 0.5 here and I go to the next field, the 0.5 is automatically added to my axial thickness, to the bottom of the tool. Since I'm doing a rough cut, I'm going to have my step down every 3 millimeters. And note every single field that I go into, by the way, note the pictures on the left hand side describing what each field does. You'll also note that our Z top level is not 0, but it's automatically put at 0.5. This is because our thickness is 0.5, so it automatically raises our top of our part by that same amount. If we continue on now to our links, we have the choices of working climb milling or conventional milling or in bidirectional. I'll be choosing to use here to work in climb milling. Now if I go into my ramping area, you'll note that we have different ways of ramping into our part, whether it be profile ramping, helix ramping, or plunging ramping. I use the helix ramping. Now I just want to go back for a moment to my general area. There's one other area which I did not mention, which is link by Z level. Link by Z level, what that does is if I'm machining over the entire part, instead of going down from 1, 2, 3, 4 and then going to the next area, it'll first machine every single area on that particular level and then go down and so on and so forth. This is good when you have thin walls and you want to keep an even amount of material as you're cutting on the sides of the walls. In this particular case, I do not need it. I'll just leave it the way it is. Another thing also in my passes area, we have something here called detect core areas. Detect core areas allows me to approach the part from the outside wherever I can. In those particular cases, it'll go in from the outside. Places where it cannot machine from the outside, such as if we look on this part over here, these areas over here, it'll plunge in with the ramping as we've described over here. Okay, let's do a simple save and calculate right now. And while this is calculating, let me just explain. There's another feature which I'd like to mention to you, something called retracts, which we'll take a look at in a moment. Retracts actually describes how we want to retract from our material to get to the next area. We have what we call the shortest route, where, as you've seen illustrated in the picture, if I'm finished over here, it'll go up exactly over the part itself to the next area to machine. This is where the rapid feed comes into play. We also have in our retracts minimal vertical and full vertical. In these cases, when it does a vertical retract, the feed will be at G0. But in our particular case, we'll be using the shortest route. Let's take a quick look at our simulation, and I'll use the Solid Verify simulation. You'll note that the tool is coming from the outside, working its way in, and taking down all the material necessary to clean out most of the rough material, as you can see here. Now in those areas where it cannot come from the outside, as you see over there, it goes in a helical fashion, as I've explained during my setup of this operation itself. Now you'll note that even though I've done a rough cut, there's still a lot of material left to be taken off because I've gone down every 3 millimeters. This would be a little bit too much material to take off in a finish situation. So our next operation, we will do what we call a rest rough machining. We'll start our next operation of HSM, and this time we'll choose the option of rest roughing. The tool I'll be using this time will be tool number 2, which is a 12 millimeter end mill with a 2 millimeter radius on the tip itself. Constraint boundaries will be the same as before. This time I will go only to middle. Now we have a field here called previous operations. In previous operations, it lists all the previous HSM operations that we've done, so that the rest roughing would know as to where to do the rest roughing according to which HSM operation. In our case, we only have one HSM operation, so that's the only one that we'll see in this particular field right now. Now in our passes, again, I'll be using a thickness of 0.5, but this time I step down, I'll have it at 1.5 millimeters. My link, I'll leave the exact same way it was before. My ramping, as the way I go down, this time, since in most areas there are no material left, what I'll do is I'll simply do plunge ramping. Now plunge ramping, although it may seem that's going straight down, what actually happens is when it goes straight down, just before it reaches the end, it does a curve into the material itself. This, by the way, is controlled by our leads, by our lead in radius, as you see here, and our lead out radius. So before it actually gets to the material, it actually does lead in with a specific radius. Let's do save and calculate. And if we simulate our part now, you'll note that in the simulation, the machining will only be done in the areas where there is material left over. Those are the only areas where it will be working. As it goes further down on the part until it reaches and into the pocket, obviously, until it finishes the part. Now if we take a look at the simulation now in the HostCAD option, you'll note again the tool is only working in those areas, as you can see by the tool paths. And you can also note that to go from one area to the next area, it is going in the shortest possible route. It doesn't go all the way back up to the top part. If I were to take the side view, it doesn't go all the way back up to the top. Rather, it only goes up to the amount that it's needed to go up, to taking the shortest possible route to get to the next area. In our next operations, we'll be doing what we call a semi-finish on the part before we do a finish. We'll be using our finish options with leaving some material left for the actual finish cut. Now, since we have on this part both steep walls also and shallow walls, we will use two different types of strategies in order to do our semi-finish. On our steep walls, we'll be using a constant Z option strategy, and on our shallow walls, such as this, our floors, we'll be using a linear strategy. Let's take a look at how we'll be doing this. We'll start a new operation of HSM, and we'll choose the option of constant Z machining. The tool that we will be using for our semi-finish will be a ball nose, a 10mm ball nose end mill. Our constraint boundaries will be the exact same way they were before. In our passes area, we'll be leaving a thickness of 0.25 millimeters, and our step down will be every half a millimeter. Now, since we'll be working on constant Z, and constant Z works best on steeper walls, we'll limit our area of work to work only on walls, as you can see in this picture, between 40 and 90 degrees. Now, in our link area, I'll use the bidirectional option going back and forth, and I'll make a little change in our leads. Since I want my leads to come straight down, I'll have this go lead in radius as 0, lead out radius as 0, and also now our horizontal leads, and I'll also have that as 0. I'll simply do save and calculate, and in our simulation you'll note that the tool is working only on these walls over here, on the steeper walls. I can change the color also of the tool if it's not bright enough. I'll simply go to my tool and change it to a different color. And if I start my simulation again, we can see it a lot clearer now. And as you can see, it's working on these walls over here, and this area over here, all the way down. And you'll note that it will not work on these areas or on these areas over here, as these are less than 40 degrees of an angle. As you can see, the simulation completed all those other areas, leaving these areas still to be machined. Now, in my next operation, again, I will use the option of a finish option. However, this time I'll be using linear machining. The tool will be the exact same tool I used before, my 10mm ball end mill. My boundary will be the same. In my passes, I'll keep the thickness the same as the other one, 0.25, and a step over this time of 0.5. But this time, I'll limit my angles from 0 to 42. 42 giving it a 2 degrees of overlap between the machining options. In my link area, again, I'll be going bidirectional. And in my leads, again, I'll change this to 0. And as we see after we calculate, we're able to see the simulation. Now as we simulate the part, you know now it's only working on those areas only. Now, if I don't want it to jump back and forth in these particular areas, I want it to go straight back and forth from one area to the next, I can make a little change in my linear options. And in my passes area, we have something called, first of all, we have pass extension if I want to go a little past, but also in my link area, in general, we have something called simple ordering. It'll go back and forth on the part. Let's take a look at how this differs from the other option that we used before without the option of simple ordering. And if we take a look at the simulation now, you'll note that it goes back and forth straight all the time. And just skipping over those areas where it can't machine. Our next operation, I'd like to go into those corners where the previous tool cannot go into to finish off my SemiFinish. To do this, we'll use the option HSM called Rest Machining. The tool that I will be using will obviously be a smaller tool, and I'll be using tool number 4, which is a 6mm ball and mill. Again, I have my constraint boundaries, but we have something else here now called reference tool. With reference tool, I can tell this particular tool that I'm working with now, the 6mm ball end mill, to which areas to consider itself areas that were not machined. And I can tell it wherever, for example, a 12mm ball end mill was not able to go in, those are the areas that you'll be working in. Now I picked 12mm, even though before I used a 10mm tool, to have a little bit of an overlap of those areas that were not able to be machined. In my passes area, again I'll put the thickness at a semi-finish thickness of 0.25. My step down, I'll put this at 0.5mm. My links, I'll be working climb milling, or I can change it if I want to bidirectional. I'll just leave it at climb milling for now. Let's simply do save and calculate. And if I look at my simulation now, you'll note that the tool is only working in those particular corners where those previous tools could not go into. Working only on the corners itself, as seen over here. We are now ready for our finished cuts. We'll start by choosing operations in the HSM, and again we'll be choosing our constant Z machining. The tool that I'll be using this time will be a 8mm ball end mill. The constraint boundaries will be the exact same thing, created automatically. My passes, since I'm doing a finish cut now, I'll be working at 0. I'll set my step down at 0.2mm, and again I'll set my angle between 40 and 90 degrees. In my link area, I'll use bidirectional. And let's do save and calculate and see what the results are. As you can see, similar to before, we're working only on those particular areas, only on the straighter areas right now, because those are between 40 and 90 degrees. Again, it is not working on these areas. I'm going to stop it now and continue to my next operation, which will be a linear operation. This time I'll simply do save and copy, and I'll change this from constant Z to linear machining. I'll keep the exact same tool I had before. My boundary is the exact same thing before. In my passes area, my thickness will be 0. And my step over will also be 0.2. Now, my angle this time, as I did in my semi-finish, will be between 0 and 42, as to have an overlap between the constant Z machining. And we have also here something I want to use called pass extension. Pass extension will allow the linear operation that when it gets to the end to go a little past that end and then go back in. And I can say, okay, go past it by 1 millimeter. As a tangential extension, means straight off the part instead of following along the part. In my link area, again, I'll be going bidirectional. And let's just take a look now what happens after I do save and calculate. If we look at our simulation, this time you'll note that the same tool is working, but this time in a linear fashion only on the shallow areas. I'll stop the simulation for now, and if I were to go to my tree on the side, to my SolidCAM manager, I'll simply click on this V block over there. This shows us exactly the entire toolpath of the constant Z, and I'll also click on the box by the linear. As you can see, the entire part has been covered. You can even see the overlap area. Now the only thing left to do as far as this part goes is these areas over here still have not been machined to its finish. This is because the diameter, the radius of these fillets over here are smaller than the tool. For this, we'll use the rest machining option. Again, I will go into HSM. This time choose rest machining. My tool this time will be a small ball and mill of 4 millimeters. My constraint boundaries stay the same. My reference tool, I'll choose a reference tool of 9 millimeters. Slightly bigger than the 8 millimeter ball and mill I use to actually machine the part. In my passes, I'll have a step down of 0.2. Now let's just do save and calculate right now. We'll note in the simulation that the tool now is only working on those areas where it was supposed to work, only in those corners. Again, if I can't see the tool color, I can simply go into colors and change the color of the tool itself. I'll change that to a darker color. And we'll start our simulation again from the beginning. And this time you'll see that it goes exactly only in those areas with the previous tool could not work, giving a very, very nice finish on those corners. As you can see, every single corner now has been completely machined. Now, although I've actually finished the part already, what I'd still like to do in any case is I'd like to add a small deburring chamfer around the edge of this part itself. This can easily be done by simply adding another HSM operation, and this operation is called boundary machining, by working only on the boundaries itself. The tool that I will be using will be a chamfer tool with a 60-degree angle at the bottom. Now my dry boundaries again will be automatically created around the target of the geometry, and if I take a look at it, by the way, now from the top view, you see the exact border of the part itself. Now, what I'd like to do in this particular case is to work on the middle, but give it a little bit of an offset of, say, 1 millimeter, so that the center of the tool is actually 1 millimeter outside of the middle of the boundary. Let's take a look at the show, and you'll note now that the center of the tool actually will follow this boundary over here. Now, we go into our constraint boundaries. Again, I use the exact same option of automatically created, but this time in my middle, just to make sure that the tool is not confined by the constraint boundaries, I'll give it a outside offset value of 2 millimeters, bigger than the drive boundary offset value. In my passes area, if I leave it the way it is, nothing will actually happen. The tool would actually just go down and just run along the exact edge. But I want to give it a little bit of a chamfer. So I want it to actually gouge slightly into the part. So what I'll do is I'll make an axial thickness of minus 0.3 millimeters. This will allow the tool to actually go further down into the part itself. I'll simply do save and calculate. And then we'll use our simulation. This time I'll use a simulation of 3D. And if I run my simulation, you'll note that it went around. I'll run it again and stop it in the middle. Move a little further up ahead. And I'll look at the tool from the side. If I look at it from the side itself, you can see that the tool is further down than the part. Let's do a different simulation in Solid Verify. You will note that the tool will go down and mill out the chamfer around the part. Let's take a look at it again in slower motion. As you see, the tool is going down and putting a chamfer on the part itself, following the border that it was given to work on, all around until it finishes the entire part, taking an exact burr off of the edge of the part itself, leaving it with a nice chamfer finish. Thank you for joining us on SolidCAM Professor. Take care and have a nice day.